I hope that from just doing these whole heap of questions, I hope that we're not just kind of practicing them, but we're sort of noticing patterns. I know Laura noticed a pattern with a particular expansion, which they've actually taken out of the syllabus now. But that's the kind of, yeah, funnily enough, right? But that's the kind of thing we're going to be looking at, right? We have these, and I've chosen these in particular for a particular reason. When I write these expansions out, okay, these are particular expansions where we can notice patterns happening. What patterns can we see happening with these particular expansions? So these are our expansions here, and we could do them kind of normally, I guess. But is there something that we notice about them looking at the two terms that we have and the result that we get? Like, look at these two. These two are very similar. What's the difference, though? There's a -6 and +6. So the only thing that's different is there's a -6 and the +6. And the only thing that's different in this part is the same thing. I won't draw that there because that might look like it's a minus. Okay. So, what is the pattern that's actually going on here? Again, have a look at the numbers here. How do 6 and 9, how do these relate to 3? 3, sorry, I can't hear you, mate. 3 times 2 is 6, cool. And how do we get 9? That's 3 squared. Okay, right. These two are what we call the perfect square expansion. If you want to think about why it's a perfect square, well, if you think about x plus 3, all squared, like what's that actually saying? Well, it's saying we've got x plus 3, and I'm squaring that, so I'm going to get the area inside this shape here. That's kind of how we think about why that name is called that. It's called a perfect square, and it doesn't matter what value of x we put in there, I'm always going to get a square number, right? But here's the expansion, and we can formalize it. I can say that a plus b all squared, that's equal to a squared plus 2ab plus b squared. Can you write that down for me? A plus b all squared is a squared plus 2ab plus b squared. And as James noticed, right, well, if we multiply this by 2, I'm going to get 6. And if I take whatever this is and I square it, right, that's how I get 9. And like I said, there's only one difference between these two expansions. Mick, what was the difference between these two again? One has a, good, right? One has a plus, one has a minus. They're still both called perfect squares though. So the only difference is one has a plus, one has a minus. So how that manifests in the general kind of form is that this is going to be minus 2ab plus b squared. Right. So box that up for me. Over there. This one's different yet again. Does anyone remember what this one's called? Yeah, Matt. Difference of two squares. And I suppose we can look at this expression and get a hint from that, right? If you look at this, we've got one square number, x squared, and we're taking away 9, right? That's another square number. So we're doing the difference of two squares there. This is another expansion that we commonly see, okay? And we can write it out in this form. So a plus b, a minus b. And so even at this point, if I was asked to factorize, even though it seems like there's nothing in common there, I can actually factorize. I can put it into brackets by writing it like this. What that's going to do is hopefully help us answer some questions where it seems like we can't factorize very easily. But we can use one of these patterns to try and do that. Right? Let's look at something like this. Okay. So immediately I'm looking at this one. Which kind of factorization thing do I want to use here, do you reckon? Or can it be factorized? Because there's nothing in common that I could take out immediately, right? Take a square out. So like kind of like try and take it out into a bracket or something, or what do you mean? So think back to when I mean take things out, I'm saying, okay, look for what's in common. Is there something in common here between these? They both have squares. They are both squares, right? But kind of like with this one here, I mean, these are both squares, but I can't really take out something from them, right? There's no common factor. Like I can't like divide both of these by 2, for example, right? If they're both squares like a law has identified, can I use the difference of 2 squares here? Yeah, maybe. I mean, there's a squared and b squared, which is what I had over here, right? But what's new about it? There's some numbers in the front. But what do you notice about these numbers? They're square numbers, right? So, in a sense, if you go back to this factorization, you say, hang on, a squared minus b squared is equal to a plus b, a minus b, right? All you need to do is try and think about what are your a and b values here. Because here, if I was to do this one here, I know it's x plus 3, x minus 3. So I'm essentially taking the square root of this, that's x. What's the square root of 9? That's 3, right? So look at this one. What would the square, I know I'm going to get 2 brackets here. The question is what goes into those 2 brackets? What would the square root of 16a squared be? 4a. Okay, right. So 4a would go here, and I've got plus minus, and then what would go in the second part? 3b, right. Can you see that? Even though we didn't have that form, we still have 2 square things, and we're taking them away from each other. That's the difference of 2 squares there. Now, Angus was asking about these fractioned ones, and we can also address those ones, right? Something like this. Now, I'm looking at this and I'm thinking, oh yeah, there's 3 terms, so it's a trinomial. I'm going to try to use my PSF method. But when you try and use your PSF method, what you're saying is, okay, I need 2 things that multiply together to give me this, and add together to give me this. And so I'm looking at that, I'm like, okay, how does that even work? Does that even make sense, right? Because when I'm used to seeing these, I'm used to seeing numbers. I can find 2 numbers that multiply to 9 and add to 6. That's just 3 and 3. But this one, it becomes a bit trickier. Now, just as a hint, this is actually one of these forms here. Which one does it look like to you? The first one, right. Okay, because these are all addition. Okay, this is a perfect square where it's all addition. So, what is this actually going to look like? Well, I know that I'm going to have 2 things squared. Sorry, I know I'm going to have 2 terms in there. I know I've got a squared there. I know I'm going to have 2 terms. I know this is addition, so this has to be addition as well. What's going to go here and what's going to go here? So I'm trying to really match up what's going on. I can see that I've got something squared here and something squared here. What's the relationship between these n terms and these 2 terms here? Have a think.
So it's like the same number, so 3 plus 3 is 3 times 3.
Okay, yep. So maybe what I want to do is to make it a bit clearer like this. So you're saying that there's the same number twice. So 3 times 2 is 6, 3 times 3 is 9. Okay. So how do I go backwards? I have to take the square root, right, for that one there. I have to take the square root of this to get back to here. Again, I have to take the square root of this to get back to here. So what's the square root of k squared? K. Okay. K. Well, and what's the square root of 1 over 4k squared? Or maybe even a bit simpler, what's the square root of 1 over 4? Is there a square root? Put it in your calculator. Check them. One on 2, right? And that makes sense, right? Because if you do 1 on 2 multiplied by 1 on 2, you'd get 1 on 4. So which brings me back to the original question. What's the square root of this then?
1 over 2k.
1 over 2k, right? Because I know that the square root of 1 over 4 is half. The square root of k squared, I already did that, that's just k. So my square root of this whole thing is 1 over 2k, which I know I can write in this form here. That would just be, because I've got these 2 things multiplied together by itself, that's k plus 1 over 2k. How would I check that's right? Expand it. Okay, I could expand it. Or, because I know this is a perfect square, I can just check using this identity. Okay, what's this squared? That's k squared. What's this part squared? That's that guy here. What about this middle term? This is 2 times a and b. And what are your a's and b's in this case? Well, it's this expression here. Right? Does that make sense? These are your a's and b's here, right? So if I did 2 times k times 1 on 2k, and I simplified that out, that would just be 2k on 2k. But that's just 1, right? I've got same thing divided by the same thing. Right? So that's how we can look at something like this, a fraction which doesn't seem like it will factorize, but we can use these perfect squares to try and do them. All right, first one. Emily, with this one here, which one does it match up with? Okay, so it's a perfect square. And how do I know that? Well, we've got that negative there, right? So hopefully we're starting to identify these patterns. But really, to identify which one it matches up with, you can pretty much just ignore the coefficients, right? You can just say, okay, there's 3 terms, it's one of those ones over there. In this case, it's got the negative. What's going to go inside these brackets? Then you can keep going. Yeah. 2x?
Yeah, 2 over.
2 over x, okay. Yeah, cool. So essentially we're saying, all right, it's a perfect square. So I know if I can just identify what a squared and b squared are, all I have to do is take the individual square roots. So what's the square root of 25x squared? Well, the square root of 25 is just 5. The square root of that is just x. And same for this one. Even though it's a fraction, I can still do it, right? What's the square root of 4? That's 2. The square root of x squared, that's just x. And I guess if you think back to surds, that makes sense. If you take the square root of a over b, it's the same as the square root of a divided by the square root of b. Okay, so we can use those surd laws to help us realize that. Or you can try to put in a calculator if it's a numerical kind of answer. This one's different. This one only has 2 terms. So Harry, which one is this going to be? What do we call it? Yeah, I didn't write it down. That's my bad. Difference of 2 squares. Write it down. Difference of 2 squares. But there's no square here, is my problem. Or is there a square? There's 2 squares. What do you mean 2 squares? Oh, right. But here I mean, right? I don't have a square. I've got a, I don't know, to the power of 4. It can be squared. How? Christian, you got an idea? Oh, x squared squared. Okay, so this is not squared right now, but something squared gives me x to the power of 4. Think back to your index laws, right? What happens when I have a power to a power? I multiply them, right? So actually, this can be thought of as x squared all squared, right? Minus 1 on 4. And then I do have that difference of 2 squares. It's whatever's inside this minus that. And we already know the square root of 1 and 4, that's just half, right? So if I want to factorize this, if I want to put it into brackets, that would be x squared plus 1 on 2, x squared minus 1 on 2, right? Does that make sense, right? So we've got those, even though it doesn't look like we have that right now, we can do a bit of creative rearranging so that I do have it in that form. Any questions about that? All good?